And the next paper for the UNLP workshop is titled Estimation of the Local and Global Coherence of Ukrainian Texts using Transformer-based LSTM and Graph Neural Networks. So Artem, are you ready to start your presentation?
Yeah, thank you. Good afternoon. I will share my screen.
Yeah, please go ahead.
Yeah.
And you have roughly 20 minutes for a presentation and then a Q&A session.
Yeah, okay, thank you. Can you see my presentation?
Yes, everything fine. Please go ahead.
Okay. So good afternoon. Let me introduce myself. My name is Artem Kramov. I am a postgraduate student at Taras Shevchenko National University of Kyiv. So because my presentation is the estimation of the local and global coherence of Ukrainian texts using Transformer-based LSTM and Graph neural networks. Firstly, let's consider the essence of the problem. The coherence evaluation of a document falls into a category of natural language processing tasks. A text coherence implies the semantic integrity of its components. It simplifies the perception of the source of an author by a reader due to the availability of logical connections between the different parts of a document. More coherent document is easier to read and understand. Let's see some trivial example in order to understand it. This slide demonstrates a short excerpt. The first three sentences are grouped around the same topic, some schedule. However, the topic of the last two sentences doesn't correspond to the previous one because it describes just weather and some opinion about it. That's why together this short excerpt is incoherent. Taking into account the variable size of human text from several sentences to several thousands of sentences and more, it is advisable to consider the coherence of a document at different levels. Local coherence implies the consistency of neighbor spans of a text, like sentences or some discourses. In contrast, global coherence implies the availability of such connections between the remote text spans within a whole document. For instance, the first three sentences and the last two sentences are coherent according to the local coherence. However, this whole short excerpt is incoherent according to the global coherence. The availability of such features of coherent document causes the utilizing of this property of a text for solving different tasks. For instance, it's utilized for the abstract text summarization in order to ensure that the generated text is readable and can be understood by a human. Detection of the symptoms of mental illness in order to detect the deviation from the topic during the analysis of speech of the patient. Creation of post-learning materials, guides, articles, or even automatic extraction of information from structured and unstructured datasets in order to reveal the text spans that contains some information like a title, short descriptions, and some others that can be understood by a human. It should be mentioned that the coherence evaluations falls into a category of AI complete tasks, artificial intelligence complete tasks. It means that the coherence evaluation cannot be solved just by utilizing some traditional classical algorithm. That's why most modern approaches are based on machine learning techniques, namely deep learning models. Most state-of-the-art papers are devoted to the analysis of English corpora. The same investigation for Ukrainian corpora is still at the initial stage and requires further investigation. That's why the goals of the work are the following: designing experimental application of the effectiveness of Transformer-based and LSTM neural networks for the estimation of the local coherence of Ukrainian text. Investigation of the connection between sentences during the local coherence evaluation, because it is really important to understand which features of sentences should be taken into account in order to estimate their consistency. Designing and experimental verification of the effectiveness of a graph neural network in order to estimate the global coherence of Ukrainian documents. Firstly, let's start with the local coherence estimation method. the input data of the method, namely an input text, are presented as a set of the clicks of fixed length, L equals 3. Therefore, the input text T is represented as a set of clicks S sub 1, S sub 2, S sub 3, S sub 2, S sub 3, S sub 4, and so on, where S denotes a single sentence. The output coherence estimation value is calculated as a product of the coherence of all clicks. That's why the main goal of this method consists in the estimation of the considered probability. In order to calculate this measure, the model based on neural network layers was designed. This slide demonstrates the main components of the suggested model. Firstly, each sentence is passed through the preprocessing block that performs tokenization, lemmatization, and the vector representation of each word of the input sentence using the pre-trained semantic embedded model ELMA. Then this set of vectors is passed through the sentence model. This component should be considered as the main block of this model because it performs the sentence vector representation according to the expected consistency of these sentences. In order to implement this block, two different architectures were utilized: LSTM cells and transformer-based architecture. As LSTM cells are widely utilized in other state-of-the-art approaches for the coherence simulation for English corpora, it was also decided to utilize the transformer architecture for the following reasons. Firstly, its availability of positional encoding and the self-attention mechanism that allows revealing dependencies between different tokens regardless of their positions within a sentence. We suppose that it might be crucial for Ukrainian corpora. Then the output vectors of sentence models are passed to the binary classifier. Firstly, these vectors are grouped into a common vector using concatenation layer, and the resultant vector is passed through the set of dense layers. The output of this binary classifier interprets the probability of the coherence of this input click. This slide demonstrates the results obtained for different sentence models based on LSTM cells and transformer architecture. In order to estimate the accuracy, two different tasks were solved. The first one is sentence ordering task that consists in the detection whether the model is able to distinguish the original version of a document from its changed version created by the permutation of sentences positions. The insertion task consists in the detection whether the model is able to detect the original position of a sentence that was previously extracted from a document. These tasks were solved on two different datasets. The dataset number 1 consists of news articles just from a single news portal. The dataset number 2 incorporates documents of different types: news, blog posts, articles of the National Academy of Science of Ukraine, Ukrainian literature. As can be seen from this table, it is advisable to take into account the word positions at first while estimating the coherence on considered datasets, because the accuracy of the sentence model based on LSTM cells outperforms the other suggested approach. Then the next chapter of our paper is devoted to the analysis of the sentence representation, because it is necessary to understand which sentences are grouped together, which sentences are considered as consistent according to our designed model. That's why all the outputs of the sentence model, namely the vectors of sentences, were projected into two-dimensional space using UMAP dimensional reduction technique. The received result is shown on this slide. So there are 5 different clusters. Let us consider which sentences each cluster incorporates. This slide demonstrates the main the central points for each cluster. After the analysis, more detailed analysis of each cluster, it can be concluded that the cluster number 1 consists of full quotes with mention of an author. The cluster number 2 incorporates just references to the source that is typical for news articles. Cluster number 3 is the biggest one and contains the sentences of different topics, politics, sports, science, etc. Cluster number 4 and cluster number 5 incorporate the beginning and the end of quotes correspondingly. That's why it may be concluded that the designed model considers the structure of a document according to the text of some training corpus at first, while estimating the consistency of these sentences. However, after the analysis, deeper analysis of the cluster number 3 that is described in our paper, it was revealed that there are different types of connections between sentences within this cluster, namely semantic connection, first-person narrative, common phrases, common dates, and so on. And that's why, despite of the utilizing just the semantic representation of discourses in other state-of-the-art approaches for the coherent evaluation of English corpora, it may be concluded that it is advisable to utilize more text features in order to improve the accuracy of the designed coherence estimation model, I suppose, for English and for English, Ukrainian, and other languages. The next chapter of our paper is devoted to the creation of the global coherence estimation method. In order to take into account remote connections between sentences, it was decided to represent an input text as a graph, where each vertex corresponds to a single sentence and edges interpret the connections between them. The main steps of the suggested method are the following: establishment of the edges of the directed graph, calculation of the weights of edges, and coherence estimation based on the graph build. In order to implement the first step, namely to establish edges, it was decided to perform the experimental verification of the effectiveness of other graph-based coherence evaluation method named semantic similarity graph on the value of its regulative parameter theta. Semantic similarity graph methods consist in the representation of a text as a graph, where also all sentences are represented as vertices, but the edge is established between two nodes if the weight of this edge is more than the value of regulative parameter theta. As can be seen on this slide, there is the dependency on the accuracy of the solving sentence ordering task on the value of its regulative parameter. And the highest value was retrieved for the value of the regulative parameter theta that is equal to 0 and 0.1. It means that it is advisable to take into account the connection between all sentences during the analysis of the global coherence of the document. That's why our text graph is cyclic and complete. In order to implement the second and the third steps, namely the setting of the weight of edges and the evaluation of the output coherence, we decided to design a neural network model based on layers of graph convolutional networks. Firstly, all node vectors are initialized utilizing the previously trained sentence model that was taken from the previously considered method. Then the update of the vector presentation of vertices according to the GCN is performed by the following equations that's shown on this slide. M sub I denotes the influence of other vertices into the current one. E sub ij denotes the weight between two vertices, I and j. This value is calculated utilizing a set of separate dense layers. The vector presentation of a vertex is performed according to the influence of other vertices, and its current state. Readout function, namely the aggregation of all vector representation of all vertices into the common vector representation, is implemented as an extra LSTM layer in order to take into account the sentence positions of the input document. The last one is the classification model, the last block that is implemented as a simple binary classifier. The output of this classification model interprets the probability of the coherence of the whole document. This slide demonstrates the results obtained for the sentence model based on LSTM model, namely local coherence estimation, and graph neural network, namely global coherence estimation method. The results obtained indicate that the local coherence estimation model outperforms the corresponding global model on datasets number 1 and number 2. However, the more detailed analysis of the overlapping percentage of correctly recognized documents for these models on the considered datasets indicate that it is advisable to consider the effectiveness of these two models on different datasets, because the overlapping percentage doesn't exceed 40%. It means that these models are able to correctly process different types of documents. That's why two different datasets, number 3 and number 4, were created from the datasets number 1 and number 2. These datasets, newly created datasets, just contained the text with a count of sentence from 3 to 6. As can be seen from the results, the global coherence estimation method outperforms the local coherence estimation method, except for one case. That's why it may be concluded that it is advisable to utilize the designed both global and local coherence estimation models for different directions. The local coherence estimation models may be utilized in order to track the change of the consistency of neighbor text spans within a whole document by the consequent analysis of this document. According to the global coherence estimation model, it may be used for more detailed analysis of some particular part of a document in order to reveal the dependency between all sentences of this excerpt, paragraph, and so on. According to the results obtained, the following conclusions can be drawn. The results of the comparison of the use of different neural network types while estimating the local coherence may indicate the appropriateness of taking into account word position within text while analyzing text spans for the coherence relation of Ukrainian corpora. It should be mentioned that we performed the same analysis for the Slavic language, namely the Polish language, and the results were the same. The analysis of sentence representation by the component of the suggested method allows drawing a conclusion about some structural consideration of sentences by the designed coherence estimation model at first. However, more detailed analysis of the biggest cluster might indicate the availability of variety of other types of connections between sentences, like semantic, common phrases, common days, common person, and so on. The negative dynamic of the change of the accuracy of the semantic similarity graph method during the increase of regulative parameter may indicate the availability of the connection between all sentences during the global coherence estimation of the considered Ukrainian language corpora. In general, the results obtained for global and local coherence estimation models indicate the visibility of the usage of them for different purposes while analyzing the coherence of Ukrainian documents, namely for the analysis of the text parts of different size. Thank you for your attention.
Thank you, Artem, for your presentation. While we're waiting for the questions, and the audience, please raise your hand if you want to ask the question to Artem. I will want to start. So, Artem, can you please jump into the slide with the model, with the architecture of your first model when you have those clicks and yeah, this one. So first, my first question, just to clarify the terminology we use. So what is the click in your paper? What does it mean?
The term click means the group of sentences of fixed length. Each click contains the sentences according to the positions in the sentence, like the first, the second, the third sentence, the second, the third, the fourth sentence, and so on.
So is it correct to say that it's a sequence of sentences which goes one after another, right?
Correct.
And you mentioned that the size of the sentences are fixed in terms of the words.
No, it was decided to. Yeah, of course, it was in order to speed up the training process. It was decided to perform some padding mechanism in order to train it using base technology, and we decided to, as far as I remember, we decided to utilize the max number of words that is equal to 40, according to the investigation of the other English corpora, that more words in a sentence is almost always can be understood by a reader fully, in a full manner.
Yeah. So have you limited the number of words in the sentence for your specific model, or we can use different lengths of the sentences?
We've limited the number of words because just for the speeding up the training process.
Okay. And probably the second question regarding the architecture, as far as I understand, you fix the number of the click length to 3, and it means that you just measure coherence within this window of 3 sentences. And obviously, if we take some news article, and as far as I understand, one of the corpora you used was Ukrainian news articles, it's easy to find the cases when these incoherent sentences would be in the different part far enough, like, I don't know, 10 sentences, for instance, or much farther. So how do you plan to deal with this? Because this kind of architecture have this limitation that we stick to this specific length, and what are the opportunities, how we can tackle this challenge?
First of all, we decided to utilize such a length according to the to other state-of-the-art papers, and in that papers different lengths of these clicks were utilized, and it was revealed that the accuracy remains almost the same. According to the detection of some long-distance incoherent cases, as we can see from the previous slide, we calculate the output coherence as the product of the coherence of all clicks. So if we'll detect that some neighbor sentences are not consistent, then the output measure of the coherence will be lower.
Okay, thank you so much. We have a couple of questions from the audience. So, Oleksiy Turuta, please.
Thank you for the presentation. I have a question on slide 7. Could you wrote about transformer-based methods. Could you say what kind of transformer-based method did you use for the part?
Yeah, thank you for your question. We have utilized just the classical approach, classical realization, implementation of transformer we used 2 encoders, and each, as far as implements, number of head is equals to 8. So we didn't utilize some already some implemented solutions, because unfortunately for that time when we started this research, such models were absent, but I know that now they're presented. So it was decided just to implement the transformer from scratch according to the original paper.
Thank you.
Thank you. And another question from Tatiana.
Yes, thank you. Thank you for the presentation. I have a question about the aggregation of the individual scores for the local model. So I think you showed that you multiply, you get these 3 scores for the 3 sentence chunks or clicks, and then you multiply them. Did you try other ways of aggregating this? Because, for example, if you think of your initial example that you showed on the slide, there's 1 break, but the other parts are locally coherent, right? But if you get this and you multiply in this very low number, you'll get a very low score in the end, right? So just a few breaks will really lower your coherence score overall. And I wonder if that's the right way to kind of aggregate these different individual scores.
Thank you for your question. First of all, we can always apply some route according to the number of clicks in order to make our value more normalized. And according to the multiplying, it was decided to utilize this operation according to other papers, other approaches, in order to reward negatively such cases when some sentence deviates from a topic. When it is necessary, for instance, it may be utilized as I said before, for detection of mental illness symptoms, when some person is talking and suddenly he interrupts his speech with other sentence that is totally with other topic. And the multiplying mechanism allows us to negatively reward these cases and to lower the output coherence measure.
Thank you.
Thank you, Artem. And I want to ask another question regarding the Ukrainianish of your topic. So your presentation seems like totally agnostic of language. You just mentioned once or twice that you use Ukrainian corpora. It would be great to see the comparison of this approach regarding different languages. So have you tried to, because I assume that you work with, for instance, English, and then tried to use it for Ukrainian. Have you tried this one?
Yes, thank you for your question. First of all, we tried utilizing the same approaches for other Slavic language, for the Polish corpora. The main difference was that for the sentence models, for the transformer-based approach, we utilized the pre-trained BERT model. And as I said, the LSTM-based approach was also better in comparison with this BERT model. We thought that it will be that the BERT model will outperform, but the LSTM model leave the best. According to other languages, we tried our other approaches to analyze to estimate the coherence of English, Chinese, and Arabic corpora. But that approaches was devoted to the analysis of the coreference resolution, the impact of the coreference resolution on coherence evaluation. And according to the utilizing of the considered methods, we decided not to utilize them on the English corpora because because the same approaches have been already implemented for it.
Yeah, I mean that you obviously you cannot, so you're not obligated to run it on English corpora, but still you can compare the results published by other authors. And also, because we're running out of time, my last suggestion probably would be, it would be great to see more information about your used corpora. For instance, you mentioned like 2 of them in one moment and 4 of them another, and on another slide. So whether they are opened, I mean, so do other researchers can play around with your corpora and replicate your results?
Yeah, unfortunately, I'm not sure that I'm able to share it in public access because it's some articles of a news portal, and it's the first data set, and the second data set was kindly provided to me by other persons that asked me not to share it with others. So I can just share it in a private mode.
Yeah, so and you understand that it's hard to estimate the quality of the results if no others can reproduce them. But you're probably familiar with open Ukrainian resources, for instance, published on Lang UK portal, and there is also a corpus with Ukrainian news texts. They just shuffle all the words and all the sentences, so it's almost impossible to figure out what are the sources. So I mean that probably for the future research, it would benefit your results if you use those open corpora. It's just a suggestion. Thank you for your research and thank you for your presentation. And